In today's video, we're going to talk about the photoelectric effect and the effects of that, or on Coulomb's law, and the relationship between photoelectric effects, and Coulomb's law, and also how Coulomb's law affects other types of forces. So let's go ahead and get started. So photoelectric effect is the emission of electrons from substances that are exposed to light. So if I give you a specific type of energy and we apply it onto any sort of atom as with a specific wavelength, you're able to remove electrons away from that atom. And so really what it comes down to is how much light is being released from that atom. And photoelectric effect really has to do with this idea of the photon effect and the idea with these electrons kind of moving up and down. It kind of also gives the idea of why is it that we get glow iron, it glows when it's heated, and certain types of light are getting emitted when things are applied energy. So talking about that specifically, it kind of relates to ionization energy, because in ionization energy, you're really talking about removing electrons away from that. So if I'm trying to remove electrons away, I have to take into account how much energy I got to put in to remove. And once that electron removes, there's some sort of light that gets emitted from that, or some sort of electron gets emitted. So the photoelectric effect is more like the result of something getting removed, while ionization energy is how much energy you need to get that removed. So that's the best way I can kind of break that down. So photoelectric effect basically refers as more energy is required to remove successive electrons from atoms. So if you start removing electrons out from these atoms, every single atom that you're trying to remove just generally increases over time. And that's one of the bases for the whole idea of photoelectric effect, is that there's some sort of energy or force that's holding these molecules together. And when they're holding these molecules together, what you end up with is a situation that creates a bind between these atoms. And this is really an effect due to Coulomb's law. And there's other parts to this that also play a role, but Coulomb's law really is the overall binding force to it. We've talked about this in the past, where we've talked about nuclear charges, we talked about orbitals and shielding, and those are really more of an effect versus the cause of the whole idea that, for example, fluorine is more electronegative than something else. It's because Coulomb's law really dictates this idea of interaction and attraction between these forces. So let's talk about Coulomb's law real quick. Coulomb's law is quantified as a general rule of electrostatics. And so electrostatics is a branch of science that really deals with this idea of electro attraction and electron repulsion. And that opposite charges attract and like charges repel. So think of like a magnet as an example. If you take the opposite ends of a magnet and you try to put them together, they may repel if they're on opposite charges, but if they're both on the same charge, they're going to end up attracting themselves. And so an electrostatic force between two charged bodies is proportional to the product of the amount of charge on the bodies divided by the square of the distance between them. So if I have a very large charge between those two, I'm going to have a larger attraction. And so if you think of it as like a number, for example, if I have a 10 plus positive charge and a 20 negative charge, these are really large numbers. They're going to end up attracting each other. And if they're very close to each other, they're going to end up attracting even more. So Coulomb's law really kind of says, all right, we've got these very big charges. They like to attract. If you reduce that distance, you're going to end up getting a lot more attraction. This kind of makes sense along with like the solar system as an example, right? As you're closer to the sun, you have a lot stronger gravitational pull versus where you're a little bit away from it. And it also has to do with the size of the planets. The sun is huge, and what that does is it just kind of pulls everything in together. So here's the formula for Coulomb's law. It's going to be FeKQ1 times Q2 divided by R2. And as you can see from here, if you have a very large Q1 and a small Q2, if you multiply these numbers together, and Q is going to be a charge of the body, for example, you're going to end up with a very, very large attraction. Now, if Q2 is very large too, and they're opposite charges, then even more you're going to have that attraction. And K is a constant that's put into here. And R2 is the distance, so it kind of makes common sense, right? That the farther this distance is, the more likely they're not going to get attracted. And this has to do with this idea of covalent bonds and ionic bonds later down the road, because again, the farther that molecule is away, they're not going to come together. Pretty common sense. But the closer they are together, more likely they're going to come together. So atoms generally tend to behave the same way as we do. You're next to a person, you're most likely going to interact with them. And when you're not, well, you're not, right? So Coulomb's law really breaks down that if the bodies are oppositely charged one positive and one negative, they are attracted toward one another. If the bodies are similarly charged, both positive or both negative, there is a repulsion that goes with it. So there's usually going to be some sort of repulsion that comes in when they have two like charges. So if I take two, for example, two electrons as an example, and I put them together, you're going to get a repulsive force according to Coulomb. While if you get two positive charges, let's say two cations that have the electrons stripped away, they're going to have also another repulsion force. And so again, just think of it as opposites attract and the same don't. And that brings us back to this idea for coulombs, as you guys can see from this diagram. Positive Q versus positive Q small, they're both charges, so they're going to repel, but you have a negative and a negative, they're going to attract, and a negative positive, sorry. And then if you go ahead and take the absolute value of that, the Q times the Q, divided by the R squared, because obviously you're not using negative charges for forces, what you're going to do is you're going to end up with that force. Now in physics, they tend to, figure out the magnitude of that direction, so how much of that force is being put out. In chemistry, all we really have to do is that there's going to be a force coming in, and that R value is going to be what creates the attraction. Now, how do we use Coulomb's law in nuclear forces? It's pretty straightforward. Coulomb's law is basically this idea of attraction. So if you have a core electron versus an electron that is on the outside, that attraction it's going to be pretty weak, because the distance is pretty far away. But if you get something where it's a little bit closer together, like an inner core electron versus a valence electron, then you're going to get a little bit more attraction. So based on Coulomb's law, the force between the two charged particles is proportional to the magnitude of each of the charges and inversely proportional to the distance radius between them. So again, the larger that charge is, the bigger that charge, that Q value is, the bigger that numerator is going to be, which means the bigger that force. So again, if I take a element like fluorine as an example, fluorine has a huge nuclear charge, and I take something like a hydrogen, which has a smaller nuclear charge, they definitely are going to have a very large attraction. That's why HF is a very, very highly electronegative molecule and very, very polar molecule. Now if we take a look at D as an example, that distance has to be close. So if I put them very close together, they're going to end up attracting to each other versus if I increase that distance. Alright, and so just kind of wrapping up that with the PEZ situation, the photoelectric effect really is this idea of PEZ, where you're really talking about electrons as photons, energy as photons, or light as photons, sorry. And in the photoelectric effect, the light is going to get ejected from a material. And this requires the photon to have enough energy to eject that electron. And when we do is we measure that using photoelectron spectroscopy, or PEZ, where we're going to be able to determine where the electron is in which orbital, and it tells us electron configuration within those atoms. So if you ever wondered where those electron configurations come from, it's because we're able to use experimental data to determine the location of those electrons. And that's a really, really important point, because if you can figure out the electrons, you can figure out the actual element that that atom represents. Right, so if I give you an unknown mixture or an unknown sample, I can actually detect the actual atom itself, and that's very, very powerful in terms of identifying unknown substances. Alright, so PEZ basically comes back down to this idea about the energy and multiple electron atoms given ionization energies, how they're close together, and talking about shells. And there's going to be another video that will talk a little bit more about PEZ, but basically it's the height of the PEZ is a signal to the relative number of electrons that gets ejected from those shells and those subshells. So be sure to check those out and you'll get to see them a little bit.